Now I'd like to ask everybody to join me in welcoming Andreas Ericsson, our next speaker.
Thank you very much. I'm going to be talking about Nagios Core 4, what's new in there, and the various improvements that have been done that will affect you as the user groups. I'm 32 years old for another month, which is good. I've been programming since I was around 7, and I work as a core architect at OP5. Core architect is somewhere between a system designer and software developer and presentation monkey or something. I am one of the co-maintainers of Nagios Core since about 2009, and I will be found at the bar in the evening. So if you have any questions you don't want to ask now or anything, just look me up there. Right. About OP5. Actually, this presentation is pretty cramped on time already, so I'm just going to say that OP5 has a lot of info at we have a lot of info at our webpage. We specialize in doing very high performance Nagios installations with our product, which we call OP5 Monitor. Read all about it. Right, Nagios Core 4 then. Sorry if I'm coughing a bit, by the way, I'm recovering from a slight cold. I'm going to discuss the goals we had when we set out to make Nagios 4. We're going to do a little bit of computer science crash course here. We're going to go through the new features and future possibilities. Actually, I think I cut out the future possibilities, but they're still on here, so we can discuss them briefly if you want to. A few of the goals that we had was that we want to make Nagios, want to keep Nagios stable. It is stable now, it's working very well. We want to increase the scalability so that we can increase the performance, basically, of all parts of Nagios so that they work as fast and as good as possible. We want to keep the simplicity. One of the very, very key features of Nagios that has made it so successful is that anyone can write a plugin. If you can write any type of scripting language or can write a one-liner in shell, then you can actually write a plugin. That is a very, very simple API that we use against plugins. And simplicity and usability go hand in hand. Without users, Nagios would die very quickly. So we have to maintain a low complexity. We have to do testing. We have to use efficient code, of course, and avoid magic as much as possible. Now we come to the computer science crash course. When we're doing algorithm analysis, we have a sort of big O notation, which we call it big O. If we want to do something on 100 elements, there are different categories that the algorithm that we use will fall into. If we have a constant time algorithm, it will take, if one operation takes 1 microsecond, this is actually a lie, there's a nanosecond, I think. Anyways, it's very, very quickly, very, very fast, and then it increasingly gets worse. When we get to factorial performance, then we have somewhere around 144 billion years, which is pretty bad. This gets a lot clearer if we compare them to each other and how fast they grow. This is only for 10 elements. I know a lot of people in here have like 5,000 hosts. I know one guy who sits around 40,000 hosts in one of his configurations. If you try to use a shitty algorithm or an algorithm that doesn't really take into account the most efficient way of doing something, you're going to end up with this peak being 10,000 trillion times taller than the small one here. We're going to see some effects of that, and there are effects of that in Nagios 4, actually, which Daniel has helped me verify. So logarithmic, screw that, actually. It's just know that there are different classes of different types of way of doing things. And some are really, really fast, some are really, really slow, and they only really matter when you get to really large data sets. If you have really small ones, nothing matters. You can write any kind of shit. I/O media comparison. When we have hard disk drives, this is for a SCSI top-of-the-line RAID 5 cluster thing, I think, has a seek time of about 5.11 milliseconds. Solid-state drives have 0.24 milliseconds, and in RAM we get down to 13 nanoseconds, which is 0.0000. Not really important. I tried to make a graph of this, But it turns out that RAM will never ever show up because it's 400,000 times faster than hard drives. So the conclusion we can draw here is that all types of disk access is really, really bad. When we need to go down to the disk to do anything, we lose instantly because it's 400,000 times slower than doing it in memory. The test setup that I used to do my bottleneck analysis had 3,000 hosts, 200,000 services, 5-minute check interval, and a really, really stupid plugin, which is called check A-OK. It says, everything's OK, and then it exits and says that everything's OK. The bottlenecks that we found were these ones, basically. Configuration parsing was a huge hurdle at first. It wouldn't even load my configuration, so I set out to fix that. Event queue insertion. This was actually, I didn't think this would be a bottleneck, but profiling of the code showed me that it was. So for large configurations, Nagios spends 99% of its time adding events. That's in Nagios 3. If we go back to the algorithm analysis, it runs in ON time, which means it looks at every event in the queue on average. Actually worst case, but it turns out that the worst case is the one we hit almost all the time. So, and it does that 676 times per second with our test configuration. But we, well, I know that the lowest bound for that is a logarithmic algorithm that only looks at a small portion of it. The macro resolution, when we're resolving macros to run checks like host address and whatever, user stuff. We also do a linear search on the macro table, and it has 150-something entries. And we do that for every macro that we have to resolve. It turns out that we're calling strcomp, which is the function that compares two strings to each other, 3,700 times per second with Nagios 3. The final one, job spawning and check reaping. It's very, very heavy on something called cache line fills, which means that the computer is trying to look something up in the really, really fast memory, notices that it isn't there, and then it fetches it from somewhere else that is a lot slower into the very, very fast memory, and then it looks it up again. That takes time. Also very heavy on disk I/O, and as I showed you before, disk I/O kills us immediately. It also lacked a bit from insufficient parallelization because only one check could be spawned at one time. Now I'm only discussing Nagios' own internal check engine, which is used when you run active checks of anything. Some sort of check engine is used for every check that is spawned, no matter how that happens. So having a good check engine is really important. If we look at how Nagios 3 executes checks, we see that it will read the scheduling queue. It will fork a child. The child writes half the check result file. Child forks again and runs shell. The shell parses the command line. The shell forks, and then it runs the plugin. Child reads the status and output, completes the check result file, creates an OK to read file, then it exits. And Nagios picks up that file from a spool directory, finds the check result file. Is it OK to read? If it is, we read the file. If it's not, we get a cache miss, and we go back to reading the scheduling queue. Otherwise, we parse the check results, remove the results, and remove the OK to read file. If we're looking at the hotspots here, the things that take a lot of time, we'll find that it looks roughly like this. The red ones show disk access. This is dark red because it's a very bad disk access. It's the worst kind, where we're looking for a file that doesn't exist. It means the kernel has to reread the directory entry from disk to see that this file actually really doesn't exist. The yellow ones are when we use very heavy system calls, where we have to fork, we create a copy of our own process, which involves copying a lot of memory, and then we start up with a new table, which involves context switches and things that aren't really important. They cost a lot of time, though, so we would like to get rid of them. Oh, this is supposed to have something with solutions first. There we go. Config parsing solution. We do it nowadays in Nagios 4. We do a depth-first search for host and service dependencies. That means we turn a quadratic algorithm into a linear one, which means that for our 20